My name is Talal AlKaissi. I'm Vice President for Space Program at Group 42, a UAE-based company in the artificial intelligence and cloud computing domain. We have recently began a new space vertical here at the company, which I will have the pleasure of leading since I recently moved from the UAE Space Agency to the private sector to lead this business. I'm joined by my colleague Abdulla Alshehhi from the UAE Space Agency. Abdulla, introduce yourself.
Hi, my name is Abdulla Alshehhi. I am a space technology senior researcher working at the US Space Agency, and I've been worked previously in previous missions, the Mars mission, and today we are glad to be here to present you with our paper on methane production on Mars.
Great, thank you, Abdullah. So I'll kick us off over here. I think it would be good to provide a little bit of context around why we decided to marry the space sector with the energy sector and come up with an idea of production for methane rocket propellant on Mars. To us, I think it's important to show that adjacent industries can benefit so much from what we do in space. And in technologies that are made for space can have real interesting ancillary benefits in terrestrial industries such as the energy industry. Specifically, when you look at previous experiences with the likes of the Apollo missions that the US have had sending astronauts to the moon, it's easy to see some of the spillover effects that has had on traditional industries that we all enjoy and take for granted today. Many technologies have been spun off from those types of investments in space, and many technologies, both that are on a consumer level or even from a life-saving level. You look at MRIs, you look at shoe insoles and Velcro. All these things had their origination as an investment that was made for space exploration. And so it's easy to see how we can try to have adjacent industries, in particular the energy industry, benefit from some of these technologies. But more importantly, there are still parts of the architecture in respect to space exploration that are missing. Today we live in a world where space has become a lot more accessible than it has been in the past, with the advent of reusable launch vehicles and the miniaturization of technology that is allowing for some very interesting types of business model innovations to be built on top of the infrastructure that's being laid out by governments and some private sector companies that are quite ambitious. For us in the UAE, a country that is new to the space sector, but definitely has come a long way since the establishment of the space agency back in 2014, we are very lucky to be part of a country that has a very ambitious vision when it comes to space. And so this is professed in the Mars 2117 vision, a 100-year plan to build a habitable settlement on Mars. And we're obviously not going to do this alone. We are looking at ways that we could collaborate with different space agencies and different countries and companies in trying to bring that vision to fruition. And so one of the industry players that we've looked at recently and are doing some very ambitious things as well in terms of their aspirations to reach Mars is SpaceX. And SpaceX have successfully in the past decade been able to reuse their launch vehicle, the Falcon 9 rocket, where they've been able to land the first stage and allow several reuses of that first stage to bring down the cost of access to space. And this is presenting a very interesting paradigm shift to what was traditionally there in the past. So if you think of it analogous to air transportation, if you have an airplane that was traveling from Abu Dhabi to New York, for example, and if every single time you flew that plane, you had to parachute out of the plane when you reached New York to land safely, and that plane was destroyed and you had to buy another plane for the return trip, the price per ticket would have been really, really high, and it wouldn't have been an economically viable type of venture. But because you're able to reuse that plane over and over again, that capital cost required to build the plane and buy the plane is amortized for a number of years, that allows the passenger ticket cost to be something that's affordable for air transportation. With rockets, that wasn't the case. What was happening with rockets is you had expendable launch vehicles, or rockets that cost hundreds of millions of dollars, that would go up and be used only once. So you would have a satellite or a spacecraft with people in it, like the one that went to the moon. And that rocket itself was never reused again. So everything from the engines, all the engineering hours, everything that was used to build that rocket, based on the amount of money spent on it, plus the time that people took to build that thing, was all gone at the end once the rocket delivered its objective into orbit, whatever that payload might be. And so what you have now with reusability is the ability to end up bringing down that cost, because you're using that same infrastructure more than once. And SpaceX are now looking at, instead of only reusing 80% with their new Starship rocket that you see over here, reusing 100% of the vehicle, and being and looking at it in a way that could be conducive to building an architecture that could bring people to Mars. So what's interesting about that is, we are very interested in Mars as well. As I mentioned, we have the Mars 2117 program, but there's also our Mars mission that was our first incremental step in that vision of creating the habitable settlement on Mars. And while this is more of a weather satellite, which is now currently en route to Mars and should hopefully arrive there in February of 2021, this will be a satellite that allows us to build a global weather picture for the Martian atmosphere, something that hasn't been done before, and something that will allow us to derive some interesting science and answer many unanswered questions about Mars. What's intriguing about Mars is that once upon a time in ancient history, billions of years ago, Mars looked very much like Earth, with oceans and rivers that flowed through. And what we want to do is try to understand better what might have happened on Mars that caused it to become what it looks like today. And so this type of a mission gets us closer to that answer, and also prepares us for the eventual human habitability of the red planet. Now, one thing that's missing in the overall architecture of trying to get to Mars, so similar to the analogy I made about the plane going from Abu Dhabi to New York, you have another issue where the payload itself, whatever you're sending into space, be it a satellite or a spacecraft with humans on it, that has to carry all the fuel it needs with it to conduct its mission in its entirety. So if the satellite is going up like what we have with Yasat and Thuraya, where they go up for broadcasting and communications, it has a certain lifetime, usually around 15 years of life in that satellite, based on the fuel, limited by the fuel that it has on board. And the same thing for a spacecraft that has humans on it, that would go for an interplanetary mission or go to the moon and come back. It'll need to have all the fuel it needs with it to be able to make that return journey. And it's very energy intensive to get out of Earth's gravity well. That's probably the most energy intensive part of space travel in general, because our gravity well is pretty strong. And so you need to be traveling at 8 kilometers per second to achieve orbit, in low Earth orbit, and then with a variety of different maneuvers to save as much fuel as possible, use the slingshot effect is what they call it, to try to get you into a trajectory where you can go into the moon or Mars. And that's why Mars missions only happen once every 2 years at the closest approach between the Earth and Mars, so that you take advantage of that type of proximity plus the momentum that you need to achieve that trajectory and be able to be captured by the Martian orbit. So the analogy of the plane, now I'm going to switch to an analogy of a car, which is something that I think we're all very familiar with when it comes to fueling the car. So imagine going from here in Abu Dhabi to Riyadh by car, 400 or so kilometers away, and not having any gas stations on the way. This is the bottleneck that we are working on right now. This is what I think needs to be solved for us to be more capable of achieving interplanetary travel in an economically viable way. So reusability is one aspect, so the analogy of the plane, but then the analogy of the car, if you had to take all the fuel you needed, you need a vehicle to carry the fuel, to carry the vehicle, to carry the fuel, till you get to a point where you're able to make it without stopping on the way. And that's a very inefficient way of doing things. And so refueling is going to be a critical element. And for the Starship project with what SpaceX is developing, they are going to be refueling in low Earth orbit to be able to then carry that spaceship to Mars. But then when you reach Mars, you don't want to have had all the fuel you need with you to escape Mars gravity well and then come back here. You want to be able to produce that on Mars, because then you can maximize the amount of payload that you take with you to Mars for the settlement or the number of humans that you're sending on those missions. So it's very important to be able to live off the land. It's very important to be able to produce in situ the types of materials you need to be able to refuel the vehicle and also for life support activities. So ISRU is a big component in terms of space exploration generally, and I think the architecture behind how Starship is being developed using a methane-based engine is one that was consciously chosen because of the ability for you to produce methane on Mars. And so my colleague Abdulla will go through the methodology of how we are gonna do that. But before that, I'll talk a little bit about the methods. So there are several approaches to obtaining this type of return propellant, and this would allow us to, through certain technologies and catalysts, produce oxygen on Mars using the Martian carbon dioxide and take methane from Earth, or produce oxygen and methane on Mars using Martian carbon dioxide and taking the hydrogen from Earth, or produce everything, oxygen, methane on Mars from the Martian carbon dioxide and water that's under the subsurface and under some of the ice near the poles on Mars. So these are the three different approaches, and my colleague Abdullah is going to take you through the methodology that we've selected for this paper. Abdullah?
Thank you, Talal, for introducing our paper today. So I'll talk about the methodology. As you know that today there are a lot of interested private companies and also space agency across the globe working to achieve this goal of landing a human in Mars. As an example, which mentioned by my colleague Talal, is a SpaceX. So there are different kinds and approaches to achieve this goal. So there is oxygen and methane, which can be produced in two different approaches, the biological and also the abiotical process. So these are two different processes. As an example, the microbes, which is comes under the biological approach, and also the chemistry related to water and rocks. So now scientists are working and considering all options, but as of today, there is no mission that went there to Mars to test or also check the possibility of having a return mission from the Martian soil. But as an example, we do have the Curiosity rover, which is currently on Mars, that was launched by NASA in 2011 and landed in August 2012. It has carried a lot of studies and it's still operational until today, but there is it doesn't have any instrument that can definitely say like whether the source of methane or oxygen can be produced in Mars in these two different approaches. However, the scientists expect that non-biological explanation are more likely and working towards understanding this approach. So if we compare today the Martian atmosphere and Earth atmosphere, the elements are like almost similar. However, when it comes to the carbon dioxide, which is the dominant element on Mars, we do have Mars atmospheres can contribute to about 96% of its atmosphere is made of carbon dioxide, which is a needed element to produce methanation. But however, when it comes to Earth, we do have the nitrogen is the abundant element which contribute on Earth to about 78%. So the atmosphere has two varying composition of elements. However, for carbon dioxide, which is the main source to produce methane, is dominating in the Martian atmosphere. Here is the methanation method. Here we show two different approaches while being in Mars and also on the lunar surface. We do need two elements to produce the methanation. We do need H2O and CO2, the carbon dioxide. So when it comes to the H2O extraction on Mars, we do know that ice mining is an example, and the valleys, and also there has been proofs and environmental studies that show that the water vapor also extraction is possible. However, when these two elements they go into the processing method by the CO2 and H2O, and to take this element and produce a pure elements of the water and carbon dioxide with untreated. So this These two approaches consider the electrostasis and methanation to extract the hydrogen, and also to take the oxygen collection. As you see on my left side, that we have the auto processing and the storage tanks. So we do know that we need some electric power generation, an example solar fuel cells or thermonuclear plants to produce the Mars and lunar processes, the anode and cathode. This will contribute to the terrestrial fuel cell application. On the other side, when it comes to the carbon capture applications, we do have the methanation, which is an example of there is a different type of reactors. There is a chemistry equation, and also we need to know also the heat exchangers and the catalyst to achieve this process of methanation. And the end, when we combine this, the H2O, the auto collection, and we'll have the methane purification, and from the storage tanks all the way to the condenser. This is another example of reducing methane. This goes into the chemistry. However, I'll give an example. So let's say we have 50 kilogram of methane, which is approximated around 3,100 moles. So to produce this in 12 hours, we do need to produce this energy to be within 10 to 12 kilojoules per second, which is approximated around 10 kilowatt. So this possible system is also can be thermally and self-sustained. The process of cooling and heating is shown also in the figure below. However, we're not going to talk a lot of chemistry. However, the overall approach of producing methane on Mars is possible. Scientists and also engineers looking into solution to do this. This will help us to achieve our ultimate goal of landing a human on Mars or return safely back to Earth. So in conclusion, my colleague Talal will continue the conclusion of our paper.
Thank you, Abdullah. So as we mentioned, I think the most important takeaway from this is the fact that we can have somewhat a cross-industry collaboration to try to bring these ideas to fruition. It's very important for us to try to ensure that we're leaning on the heritage and the strengths that we have in the oil and gas sector and the mining sector to allow us to further develop and enhance our space capabilities, and vice versa as well. I think the more we invest in space, the more we find technologies that are applicable in the terrestrial energy and mining sectors that could be game-changing as well. So I think it's very important to have those two correlations. If we can go to the next slide, I definitely want to, number one, thank our co-authors who aren't with us, the Dr. Prashant Marpu from Khalifa University, but particularly also Martin G from the UAE Space Agency, who really put together a big component of the technical angle in this paper. But we also had some very key contributions from industry experts all over the world that helped us with formulating our ideas in terms of what's possible here. Bob Zubrin, who's the founder of Pioneer Astronautics and the author of Mars Direct. Dallas Bienhoff from Cislunar Space Development Company. Dylan Taylor, the founder and CEO of Voyager Space Holdings. And then on the UAE side, and a great example of cross-industry collaboration, we developed a working group at the UAE Space Agency with both the R&D division at ADNOC and the Mubadala Energy team, and we had two very notable contributors to this report from those two organizations, Adil al-Nasr and Mohammed al-Mahmid, who really played a critical role in getting us to where we are with this paper, and we're hoping to build on that in the future. And then last but not least, three other colleagues from the UAE Space Agency, Fahad al-Meheri, Khalid al-Awadi, and Dr. Fatma al-Aidarous. So thank you very much for your attention. I'm hoping that we can interact soon on ways we can continue to optimize R&D efforts between both the energy sector as well as the space sector here in the UAE. Thank you.